We've got more details about upcoming NASA cuts. The first evidence of life on an exoplanet? Is the entire universe spinning? How global warming could reduce room for satellites? And in our free Patreon edition of Space Bites Plus, a new way to search for life as we don't know it. All this and more in this week's Space Bites. About a month ago, we reported that the White House administration was planning a series of cuts to NASA, specifically targeting the Science Mission Directorate. And thanks to some incredible reporting from Eric Berger over at Ars Technica, we have a much better idea of what seems to be coming down the pike. So the White House has submitted their proposed budget to Congress, and then the next step is that they're going to work together and then ratify it or overturn it, or who knows what's going to happen. What it looks like right now is that the White House is asking for a reduction of NASA's budget by about $5 billion. So normally it's $25 billion down to about $20 billion. And there will be cuts across the board, but really the bulk of the cuts are going into the science division of NASA. And this is where you have all of the planetary science, astrophysics, earth science, things like that. And so specifically, it looks like there's going to be a 2/3 cut to astrophysics, a 50% cut to heliophysics, a 50% cut to earth science, and then a 30% cut to planetary science. And so what are the implications of this? Well, a bunch of missions will just go on the chopping block. So for example, the Nancy Grace Roman Telescope, which is largely complete and is due for launch in about 2 years, that would be canceled. Mars sample return mission obviously would not be able to proceed. The Da Vinci mission, which is due to fly to Venus, would be canceled. And then there's just going to be a whole bunch of other cancellations across Earth observation missions, things like that. I mean, there might be some other missions that will still be able to proceed, but it's mostly going to be in maintenance mode at this point. You're still going to be able to maintain the Hubble Space Telescope, James Webb, other existing missions, but there isn't a lot of room left to build and develop any new missions. I think it's really important here to not panic. None of this has been officially confirmed and ratified. This is the proposal from the White House. This is what they want to do. And then it's up to Congress to approve this budget, and then we'll have to see which missions get cut. But if it is $5 billion off of NASA's budget, something gets cut. So again, right now, this is what they want to do. And then once we know the final outcome, I will be reporting that as well. But I think we should learn now in the coming months how this is all going to play out. But again, highly recommend go check out Eric Berger's reporting at Ars Technica. A potential biosignature on an exoplanet. So I'm sure you have seen the news already that came out just a couple of days ago, and people have been sending me emails. When are you going to report on this? And it's kind of complicated. We have already reported on this many times, but this is sort of a new update to an unfolding story. So the announcement, the thing that you're probably reading, is that astronomers have detected the presence of a potential biosignature molecule in the atmosphere of the exoplanet K2-18b. And this is a planet that we have been watching for a long time. There's been a lot of really interesting observations. And in fact, this initial detection of this dimethyl disulfide was made several years ago. And dimethyl disulfide is really interesting. We'll call it DMS from here on out. It is a molecule that is in the atmosphere of Earth, and it is produced by life, mainly by marine phytoplankton. And so the fact that it exists in the Earth's atmosphere, only produced by life, means that if we find it on another world, that is a very exciting discovery. And originally, astronomers had found it, but just a vague detection. They came back around, and the new announcement is that they've done a better observation, and they've found it now with a 3 sigma certainty. And that is like a 1 in 1,000 chance that it is not there, that it's a statistical accident. And they also found it with a different instrument on James Webb. So originally they had found it with NIRISS, which is one of the instruments on Webb. This time they found it with MIRI. And so a confirmation with another instrument is great. So How should you feel? And I feel like at this point, you're running a simulation in your mind about how Fraser would report this story. And if your answer is skeptically, that's the right response, which is obviously this would be incredibly exciting if true. But there are a lot of reasons why this is a very tentative observation and is by no means indicative that there is life on this planet. Now, there's a couple of things that are really interesting about this. One is that this world is very big, but its actual composition isn't entirely known. One possibility is that it is one of these Haitian worlds. Haitian? Ocean? Haitian? How are we describing it? Haitian world? Haitian world. Ocean, Haitian. Okay, it's possible that it's one of these Haitian worlds. So in other words, you've got like a large planet that is covered with a thick layer of water, like potentially hundreds of kilometers of thick. And then surrounding that is a thick atmosphere, an envelope of hydrogen. The hydrogen acts like the best greenhouse gas, keeping all of this warmth in the planet. And that allows planets with this kind of composition to be much farther away from their planet. It extends the habitable zone dramatically. And so astronomers have thought that this world is one of these Haitian worlds. And that then you've got this thick, giant ocean. There could be tons of marine phytoplankton down there. It's surrounded by this atmosphere of hydrogen that could protect it, keep it warm, and then that would allow this chemical to make it out into the atmosphere. But another completely viable explanation for what you're seeing is in fact that it is covered in lava, that it is a magma world, and that there is ways that you could get dimethyl disulfide put into the atmosphere of this planet purely through geological processes. So it is not a definitive smoking gun biosignature, but it is a very interesting discovery. Now, the researchers acknowledge all of this, and they say that, the next step is to do more work with James Webb, this time asking for upwards of 24 hours on the telescope that would then allow them to do a much more definitive. Maybe they can get to 5 sigma, but still, that doesn't necessarily tell you that it's life, just that you've got the presence of this chemical, which is very exciting. And, we think about other examples of potential biosignatures that have been detected. We've got the detection of phosphine over in Venus, that astronomers still argue about whether or not that was actually detected. You got the detection of methane on Mars that was found by Curiosity. Is that life? And those two planets are right beside us here in the solar system compared to K218b, which is many light years away from us. So this won't be the end of this conversation, but I think, we should all just enjoy the process, watch as more data are gathered, as we get new observations, people come up with new theories, they test out the different ideas, and maybe we'll find out that this is the first planet that life was discovered outside of the solar system, and maybe it will just become another data point in our ongoing search for life in the universe. Jupiter's atmosphere is wild. Jupiter is a bizarre place. And, when you look at Jupiter from orbit, when you look at it in a telescope, you see these clouds, these storms, these bands across the planet, and it feels sort of familiar to the Earth, and yet clearly it's an alien world. But for Jupiter, its atmosphere really is just skin deep, that those cloud formations, those storms that you see on the surface of Jupiter really only go down a few tens of kilometers, 20 to 30 kilometers at the most. And that underneath that, you have a vastly more complicated and weird atmosphere. So first you got to understand the composition of Jupiter's atmosphere. It is made of hydrogen and helium, and then it has other stuff in it. Ammonia, water vapor, other chemicals that turn into gas. These are mixing up and rising and falling and going through these weird atmospheric cycles on Jupiter. Over the last couple of years, astronomers' understanding of the atmospheric composition of Jupiter has changed, and that's thanks in part to the Juno spacecraft. Instead of finding evenly distributed ammonia in the cloud tops of Jupiter, it found that it has blobs and chunks and places where it's higher density and lower density. What this means is that there are storm system, convection cells underneath the cloud tops where blobs of ammonia are rising and falling inside the upper atmosphere. And in fact, it gets so weird that astronomers think that you've got what are called mush balls made of ammonia, where you've got ammonia and water mixed together, and then it's surrounded by this shell of water ice. And these things are formed high up at the colder temperatures close to space, and then they fall like hailstones inside Jupiter, connected to storms where there's like lots of lightning activity. And these mush balls, as they fall, they go down into Jupiter, but there's no ground. And so they eventually heat up, they're torn apart, they get added to these convection cells, they rise back up to near to the top of the clouds, and then they go through this cycle again. And so scientists have been modeling how these cloud formations work and have really dialed in and simulated what is probably going on inside to match what we see on the cloud tops. And it's believed that these mush balls are probably the way the weather works on all of the giant planets in the solar system. So both Saturn and Uranus and Neptune, as well as Jupiter. And in fact, this is probably the process that is happening on all giant exoplanets out there across the universe. So it's really interesting. We can take this, very faint data from Juno, extrapolate what's going on underneath the surface of the atmosphere, and then see how this could play out across the universe. Is the universe spinning? And here's one of the other stories that people have been requesting that I do a story about. At this point, you're probably familiar with the crisis in cosmology, the Hubble tension, where the expansion rate of the universe seems to be changing based on how we measure it locally versus how we measure it in the cosmic microwave background radiation. And there's been a lot of ways to explain the Hubble tension. Maybe it's a measurement error. Maybe there are new physics that we don't understand. And then maybe it's that the amount of dark energy in the universe has been changing over time. But we got a really interesting new theory that came from the University of Hawaii at Manoa. And they propose that if the universe was rotating, that would explain the change in the expansion rate over time. And so you can kind of imagine, right? If the entire universe was rotating, it doesn't have to be very fast. Like if it took about 500 billion years to turn once, then that would explain this change in the expansion rate from the beginning when it was smaller to where it is now, which is much larger. And this isn't a new idea. Einstein considered this 100 years ago. And in fact, a mathematician named Kurt Gödel came up with a model and did the math for what would happen if the entire universe was rotating. It had some really wild implications. That distant galaxies would have a rotational bias, and we'll put a pin in that because we're going to want to talk about that in a second. That light would randomly polarize, and that in fact you would get these time loops in the universe where you might be able to go and actually meet yourself. And so the researchers at the University of Hawaii, they took this model of the universe and they set it spinning, and they found that it had a really good match for the observations. But like, what does this even mean? So if the universe is infinite, how can an infinite universe rotate in a finite amount of time? That's very weird. But even if the universe is finite, does that mean the universe has a center? So there's a lot of sort of bizarre implications of this idea. But it does match this other observation that we had been talking about a couple of weeks ago, that astronomers have used James Webb, looked out to the very edge of the observable universe, and seen that spiral galaxies are more commonly turning in one direction than another. And one of the possibilities that would explain that would be a rotating universe. So it is a cool idea. And it is just theoretical models that could potentially try to explain the observations, but it's fun to think about. And so we've got a really great story from Dr. Brian Koberlein on Universe Today. And he's an astrophysicist. This is his specialty, and so he gives some great explanations. Every week, we give you a chance to vote to tell us what you thought was the best space news of the week. And the winner this week was the relatively close supernova that's going to go off in 23 billion years. So thank you everybody who voted. Now, we will post the new poll to the post tab on YouTube within about 24 hours of when we do this show. So if you're just scrolling on YouTube and you see the poll show up, Take a second, give us a vote. Of course, the best chance, subscribe to the channel, click on the notifications bell, and then just train the algorithm or be trained by the algorithm for these votes to show up. Global warming means less room for satellites. So while global warming wreaks havoc down here on Earth, it looks like it's going to have some implications for the future of spaceflight as well. And the results of this are a little counterintuitive. So we know that as we put more greenhouse gases into the atmosphere of planet Earth, then that raises the temperature of the atmosphere, but it raises the temperature of the lower portions of the atmosphere. The upper level, the troposphere and the exosphere, those will actually get a little bit cooler. And we know that as temperatures rise, gases tend to expand. You're going to get the lower levels of the atmosphere growing slightly, but the upper levels, the places where satellites are tending to orbit, will get smaller. And so we've got all of these satellites that are in this 500 to 1,000 kilometer altitude above the Earth, and they are passing through faint gases surrounding planet Earth. And so if the troposphere and the exosphere become less dense, if they sink down closer to planet Earth, then they're going to provide less drag to these satellites. And in fact, the satellite operators depend on this drag to bring down space junk and to deorbit satellites after their lifetime is complete. And so if you don't have this mechanism that is causing drag to the satellites, then they're going to stay up there for longer. They're going to interact with each other. They're going to crash. You're going to get space debris. The space debris isn't going to clean up. And so a new paper calculates that in fact, as we get more global warming down on Earth, then we'll actually be able to launch less satellites over time because they won't be able to be deorbited once they're done with their life. So it's a weird implication of global warming, and not surprising that we're going to find more of these over time. And the full story about this is pretty interesting. It's by Alan Versfeld on Universe Today. The missing infrared light of the universe found. So there are a bunch of mysteries in astronomy, and dark matter, dark energy. Why is there more matter than antimatter in the universe? But one that astronomers are puzzled by is the energy budget of the universe, how much optical, ultraviolet, infrared light there is in the universe. And the one that's been missing is the infrared light. But now astronomers think that they've found it. So they used an old survey from the Herschel Space Telescope. And this was an infrared survey telescope, similar to James Webb, not as large, but able to look into the near and far infrared. And they took one survey that was incredibly deep, sort of like a Herschel version of the Hubble Deep Field. And they looked at this one region that looked like just a mass of galaxies, and they were able to use algorithms to separate the galaxies in this field so they could identify which one were galaxies, which are the gas surrounding those galaxies. And then they were able to calculate how much of the light was coming from these galaxies that was then getting absorbed by the gas and dust around those galaxies and then be re-emitted as infrared light. And when they were able to make all these calculations, they were able to significantly fill this infrared light gap in the universe's energy budget. So another mystery partially solved. And we've got a great story about this by Mark Thompson on universetoday.com. A magnetar on the move. Magnetars are a type of neutron star, and they are extreme. So magnetars are surrounded by these incredibly powerful magnetic fields that are so powerful, you've probably heard this said, that if you get very close to them, they would tear you apart at an atomic level purely through the magnetism. And so magnetars are this first brief phase caused when stars detonate as supernova, and they don't last long. Like typically they only last for a few tens of thousands of years before they settle down and they switch over to become a pulsar or a more regular neutron star. And so astronomers back in 2008 found a magnetar, and there aren't a lot of them out there. They know of about 30 magnetars total in the Milky Way. And they found this magnetar was very close to a supernova remnant. And so the assumption was, okay, this is the neutron star left over when this supernova went off about 20,000 years ago. Well, thanks to Gaia, they were able to measure the movement of this magnetar, and the math didn't work, that it couldn't have been the source of that supernova. And so there are some other ways that you could get magnetars as well, not just large stars turning into neutron stars. You could get a collision of two neutron stars turning into a more massive neutron star and not going fully into a kilonova. Another possibility is that you get a white dwarf that is feeding off of a companion star, and it doesn't have exactly the right conditions to turn into a type 1a supernova, but it can turn into a magnetar. And so there's all these different mechanisms. So now that they know that this magnetar isn't connected to that supernova, now they can explore some of these other ideas and try to figure out what caused it. Pour one out for Gaia for helping to track down its motion. Next up, I've got a couple of images that I want to show you. First, this is an image of the planetary nebula NGC 1514. This is what you get when a star like our sun reaches the end of its life. It puffs off its outer layers into space, and then all that remains is the white dwarf. And these outer layers expand outward, illuminated by the white dwarf, and you get these really interesting features. The ring nebula, the helix nebula, there's a lot of these planetary nebula. And this one was first seen by Herschel, the astronomer, not the telescope, in 1790s. We've known about this for a long time. And we've had pictures in various wavelengths taken of this nebula, but now we've got a new picture by the James Webb Space Telescope. And just look at the detail in this nebula, in this really bizarre shape. And what's really cool about these planetary nebula is every one of them is different. And it seems to be some kind of interaction either between a star and a binary companion, or just like some asymmetry in the way the star evolves over time. And so you get these weird, interesting shapes with each one. But it's such a beautiful picture. And we've got a cool story about that by Evan Goff. And next up, we've got some 3D versions of astronomical objects. And these were created using data from the Chandra Space Telescope. So you've got 4 objects that they modeled. 3 supernova remnants. There's been a lot of supernova remnants in this story today. And then 1 T Tauri star, which is a very young star that's just starting to form, has its planetary disk around it. They were able to take the observations from Chandra and then use that to model what these objects look like in 3 dimensions. And so they've shown some video of what these look like as you rotate them around, but you can actually download the underlying data. You can even like make a 3D printed supernova remnant if you want. While you're watching this week's Space Bites, I am writing my weekly Guide to Space newsletter, and that contains all of the stories that we're working on Universe Today for the week. For example, a roadmap for obtaining the first sample return from Mercury and Venus, and that's a story written by Lawrence Tognetti. Astronomers push Webb to its absolute limits to visualize the most distant galaxies ever seen, and that's a story by Matt Williams. Frozen lava domes on Europa could be future habitats for astronauts, and that's a story by Mark Thompson. And then finally, it's time to build a space telescope interferometer, and this is what could be the first step. And that story was written by Brian Coberline. So if you want to find out about those stories, the most distant galaxy ever seen, the domes on Europa, you're going to want to sign up to my weekly email newsletter. I send it out every Friday. It goes out to 70,000 of my closest friends. It's completely free. There's no ads. And I write every single word. Go to universetoday.com/newsletter to sign up. As you probably know, I hate ads, and we don't put any mid-rolls into our videos here on YouTube. We don't put any ads into our newsletter, into the website, into our podcasts. We have to put in the minimum amount of ads that YouTube forces us to put. And I want to provide all of my content with no ads at all if I can, and make it publicly available to the world. And that is only possible thanks to our patrons. And as a reward for getting people to watch our stuff over on Patreon, we've got a longer version of this exact same video with 1 additional story all about ways to search for life as we don't know it on other worlds. We call that Space Bites Plus. So check that out at patreon.com/universetoday. But I will put a link in the show notes so you can go and watch that. It's completely free. don't have to sign up. You can just watch it and get the extra story. I'm going to talk about a new telescope that I just bought, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Carradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Giltona, David Matz, Dustin Cable, Evan Perot, Greg Feely, Hen Schultz, Hudson Moore, Jay Grave, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Modzo, Paul Robach, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. So if you notice that you had cloudy weather for the last couple of days, that's my fault, and that's because I bought a new telescope. I bought a Seastar S50. This is not a sponsored ad. I bought this with my own money. And that's because I've just been seeing a lot of news from a lot of people that they've been using these Seastars, and they are a relatively affordable telescope, an automated smart telescope. And they're producing some really amazing pictures. Like if you do a search on the internet for the Seastar S50 and look at some of the pictures like the Orion Nebula and various galaxies, it's amazing. And the size of the lens is very small. I don't have it folded out right now, but it's about this big, 50 millimeter lens. And yet it has this automated control that allows it to look at objects and stay locked onto them for long periods of time. You can give this thing a plan, go to bed, wake up in the morning, and it has been doing astronomy for you all night, taking pictures. So very cool. I'm just getting to know it. A lot of people have been proposing that I switch it into the equatorial mode versus the altazimuth mode. There's a lot to learn about this. And so hopefully, as I learn more about it, I will share, and you will be able to do some astrophotography through me as I learn to use this telescope. All right, I'll keep you posted. Thanks everyone, and we'll see you next week.